Welcome back to CS 520. In this session, I want to talk about virtual memory. Motivation for virtual memory is to allow programs to exceed the size of physical memory. In fact, this virtual memory changed my life. When I was a graduate student, I had some ideas about how to build compilers, but the department I was studying in only had a machine at the time with 64K, and my ideas were going to require a lot more memory than that. So I started looking around at how to deal with this, and the solution at the time was to use what was called memory overlays. So the programmer would actually divide the program up into pieces, and there was library calls that you would make to actually pick up a piece of your program and move it out of memory and replace it by something else off of disk, and then continue the execution of the program. So you would physically control the movement of pieces of your program to and from disk. After looking at this for a while, I decided, getting my PhD just wasn't worth it. But luckily, my department head came up with money to buy a VAX 780 machine made by Digital Equipment Corporation, a now defunct company, and it had virtual memory. And so I decided to go ahead and finish my PhD after all, when I was able to avoid all the overlays, having to do them by hand. Instead, the system would automatically handle programs that were bigger than the available physical memory. So that's one goal for virtual memory, is we want to be able to run programs with memory demands that are larger than what we physically have in our computer. Second goal, it would be to better support multiple programs running at the same time and sharing physical memory. We want to make efficient use of resources, and we want to do protection of pages, protect our parts of the program from somebody else's perhaps malicious program. Okay, I'm going to be talking about memory caches later, and even though virtual memory and memory cache technology is very similar, unfortunately the terminology is different. So when we talk about caches, we talk about blocks, and the term when we talk about virtual memory is pages. And in caches we'll talk about misses, and in virtual memory we'll talk about page faults. So I just wanted to let you know that up front so you can translate that back and forth. The concepts, though, are the same, or very closely similar. All right, so here's the basic picture for how virtual memory works. At the top is an address that, from the programmer's point of view. So this is an example using a 32-bit address. So the programmer views the program is using these 32-bit addresses. As we'll see, the address is divided into two sections. One is called the virtual page number, the top upper bits, and the bottom is the offset in the page. The offset part just gets carried straight through to the physical address, which I've drawn at the bottom here, which notice is shorter. It's only 30 bits, indicating that there's smaller physical address space than virtual address space. And the magic happens here. The virtual page number is translated into a physical page number. Okay, and again, notice you have more bits for the virtual page number. So it could be that at certain times virtual pages are not going to be actually mapped to physical pages. Instead, they'll be mapped to locations on the disk. Okay, so in this example, I've got 12 bits for the page offset, which means the page size is 4 KB. Usually this page size is tied to your disk block size or some multiple of the disk block size. This leaves 18 bits in the physical address for the physical page number. So the physical memory maximum is just going to be 1 gigabyte, a 30-bit address, and the virtual memory maximum is going to be 4 gigabytes, corresponding to a 32-bit address. Okay. Again, virtual memory, is backed up on disk. If a virtual page doesn't fit in physical memory, it's stored on disk. So there's a large miss penalty, right? The disk, again, as I mentioned in an earlier lecture, the disk has a physical mechanical component, the spinning of the platters. So it's very, very slow relative to the electronics of memory. So we're going to have a large miss penalty. So what does that imply? Well, it means we're going to have a large page size, because when we actually go to the disk, it's going to be slow, so we're going to read a lot. We're not going to just read one byte or one word. We're going to read a full disk block. So we're going to have a large page size. Also, because there's this mechanical component, it's really slow, we can get software involved in handling the misses. Because the time to run some software relative to the time for the mechanical components of the disk is very, very small. So we can afford to do some things in software here. Also, because writes, disk accesses, writing to disk is very, very slow, we're going to accumulate writes in memory and only send them to disk when necessary. So when we talk about caches, we're talking about write-through caches, and we won't want to do that. We're not going to both update memory and write to the disk. Instead, we're going to accumulate the writes in memory and only write them back when necessary. And because the miss penalty is so large, reducing page fault rate is really important. So those are all things that come about because the disk is slow. One thing we can do to help with the page fault rate is to actually use an associative mapping. We can allow a virtual page to be placed anywhere in physical memory. Again, you might think of a simpler strategy where a physical page always goes to the same a virtual page always goes to the same physical page. That's called a direct mapped approach. But having associate mapping and not having any restriction over where the page is placed in physical memory gives us more flexibility, and we're looking for all the angles we can possibly have to try to reduce the page fault rate. So how can we implement an associative mapping? Well, what happens is you use a page table which actually contains the mapping and can be dynamically changed. And every program has its own page table, and the page table is in memory and is pointed to by a special internal register, the page table register. Let me show you a picture here. So at the top of the diagram we have the virtual address. Again, it's a 32-bit address using the same example from before. It's divided into a page offset and a virtual page number. The page offset, as I said before, is just going to be brought up, those bits are just going to be brought down and dropped into the bottom part of the physical address. But we have this page table register that points in memory to this table, the page table, that will do the mapping. So the virtual page number will be looked up in this table, and its entry in the table will contain a bit that indicates whether that virtual page number is valid. In other words, whether it's currently in memory or not. And if it's in memory, then we can take the other bits out of this table entry and use them as the top part of the physical address. They're the physical page number. So the table does the mapping. We come in with the virtual page number, and out comes the physical page number. Notice that if the valid flag is clear, in other words, the virtual page is not in physical memory, then we can take this part of the table and have it store the disk location of the page so that we know how to satisfy the page fault. We read that block off the disk. So when a page fault occurs, the operating system is given control to get that page from the disk. Again, we can afford to do this because the disk is so slow, so having the operating system run some code is really not, is immaterial relative to the slowness of the disk. The key problem, again, because we've decided to use an associative mapping, is if all the pages in physical memory are in use, then when a page fault occurs, which one should be replaced? Because again, we have, with an associative mapping, we can replace any of the physical pages. Well, yeah, the temporal locality argument phenomenon would argue that we want to replace the least recently used page. By the way, least recently used is often referred to by its acronym LRU. Right? If the page, by the concept of temporal locality, the page that we should replace is the one that we haven't used for the most time. That's the least likely one to be used next. Notice that in this world where we have big pages, spatial locality is basically handled by fetching the whole page when we go to disk. So we sort of prefetch, we just want one piece of that page, but we go ahead and prefetch all of the page, everything nearby. That sort of picks up spatial locality. But the replacement algorithm is motivated by this temporal locality. You know, what we expect is least likely for us to use again is the item that we haven't used for the longest amount of time, the page that is least recently used. So we can approximate which page is least recently used by the following approach. We could keep a reference bit for each page. So again, if we go back to the page table diagram, I could add another field to a page table entry. Right, I could add another field in here, which is the reference bit, which simply tracks whether a page has been referenced or not. So every time we access the page, we set that bit. And the trick here is the operating system will periodically clear all the reference bits. So it'll periodically come through and just clear everything. And then when we have a page fault, we simply look for a page with a clear reference bit. A page with a clear bit is among those that's least recently used at page fault time. So it's not going to tell you exactly which one is least recently used, but it will allow you to choose one from a set of pages that haven't been used for some increment of time, and therefore are good candidates to be replaced. So this is a quick way to sort of approximate least recently used. Okay, let's talk a little bit about writes. Basically, the terminology is that the virtual memory systems typically use a write-back approach rather than a write-through approach. So again, as I indicated before, they're going to accumulate the changes in the page in memory, and they only write back the page only at replacement time. So only when they have to do they write it back. This means that there's periods of time then when the disk copy and the memory copy are out of date. But again, because of the cost of writing to a disk, we tolerate that. Again, it requires another bit to sort of be tracked in the page table as to whether a page has been modified or not, because we don't want to do that disk write if the page has not been modified. Okay, so again, the approach here, the write back approach, is we accumulate the changes. We only write back the page when we need to replace the page with another page in memory. And we have to keep a dirty bit to keep track of whether a page has been modified since it was loaded from the disk. And we only write it back if it's been modified. At this point, I just want to recommend a book for you to read. There's an interesting book by Tracy Kidder, who's written a whole series of these books where he follows around somebody in a particular profession like teaching, or in this case in the computer industry. He embedded himself, I guess that's the term we use nowadays, he embedded himself with a computer engineering design team that was working on a new computer that had virtual memory. This was a mini computer back in the 80s. And it was the company, which is now defunct, was called Data General. For those of you that work at the IOL, the building that you work in on Technology Drive out there was originally constructed by Data General. And they made this mini computer. And in the book, he's talking about Tracy Kidder's who's embedded with these engineers, and they're trying to design this computer and bring it to market. And he has a very interesting anecdote in there about a very intense time for the engineering group, because they had a bug actually where their dirty bit was not always being set appropriately. And so they'd accumulate changes in memory, but when they wrote the page back, they wouldn't always write it back even though it had changes. So this led to very obscure bugs, as you might imagine, right? Some updates to memory were simply lost. Anytime, not anytime, but occasionally when you were pushing a page back to disk and then reloading it later, you would notice that you had lost some updates. Anyways, the book talks about this and a lot of other interesting aspects of working in a technology company under business pressure to bring products to market as quickly as possible, but of course needing to do that with as few bugs as possible. And I think it's a good book for people to read who are thinking about getting into the technology field, and just to see what life is like in the real world. So I would recommend that. The name of the book is called The Soul of a New Machine. Again, it's from the 80s, but I think a lot of what the book talks about is quite timeless. Okay, back to the subject at hand of page tables. There's sort of a, one aspect of this video lecturing is there's no feedback from the audience, but you may be out there sitting wondering, gee, there's a problem here, right? The page table, I said, sits in memory, and we need to access the page table in order to do the translation of the virtual page number to the physical page number. So, isn't that a little crazy? Because we're going to have a page table in memory. That means each memory reference requires two memory operations, right? We've got to read the page table, and then we've got to read or write the requested memory location. So that doesn't sound good. Every memory reference now takes two memory operations. Well, the solution here is to employ a special cache to remember those recent virtual to physical page mappings. So in a very high-speed memory, a special cache, we can keep recent mappings of virtual to physical page numbers and reduce that rather than being twice, two memory operations for every memory reference. It's 1 plus some small epsilon, depending on how well this cache works. This cache has of course, a complicated name, as we like to do in the computer industry. It's called the translation lookaside buffer, and usually most people talk about it as the TLB. Okay. Now, let me go back to that first one of the early slides. I think there's a couple of items left I need to talk about. It's really the support for multiple programs sharing physical memory. And one of the items is memory protection. Right, now that we have this page table data structure, and we're already talking about having it store reference counts and valid flags, we can add other stuff in there too. Why not? And so what we can do is for each page, we can record protection information. For instance, the page might be read-only. The page might be execute and read. The page might be read and write, but not execute. So we can add some control in there and have the hardware checking it. This can actually feed into the second point, which I listed first here for efficient use of resources, because now I can do things like have two programs accessing the same physical page with two different virtual page numbers, right? So for instance, we're all using printf. Rather than both of us loading printf into our own separate physical pages as we used to do in the old days before there was virtual memory, now we can use the page table mechanism, because there's no reason why we can't have two programs page table map virtual pages to the same physical page. Okay, so we can use the page table mechanism to efficiently share memory. And the protection helps us do that because we can make sure it's read-only, for instance. We don't want one program changing a page that we're sharing, which would disturb, obviously, the other program. So the page table, again, can be utilized for protection, which can help us do efficient use of resources. Okay, that's a quick spin through how virtual memory works. Let's stop here.